Hello, welcome to the organic chemistry where our focus is going to be on hydrocarbons. So hydrocarbons consist of a skeleton structure of carbon atoms connected to hydrogen atoms. This is just one of the examples. When you look at this compound, what comes to your mind is the chemical bonding. So in a chemical bond, atoms tend to lose or gain electrons in order to acquire an octet state. So something like carbon atom has 4 valence electrons. To acquire an octet state, it needs 4 more. So it's going to form a bonding capacity of 4. In other words, it's going to have 4 bonds to another atom it can share electrons with. So carbon is said to have a bonding capacity of 4. Nitrogen has 5 valence electrons, so it needs 3 more in order to acquire an octet state. So then nitrogen has a bonding capacity of 3. Oxygen has 6 valence electrons, so it needs 2 more electrons to acquire an octet state. So what's the bonding capacity of oxygen? Well, your guess is as good as mine. It's going to have a bonding capacity of 2. Fluorine has 7 valence electrons, so it needs 1 more. So therefore, something like fluorine is going to have a bonding capacity of 1. So we can look at the periodic table and predict the bonding capacity of an atom depending on the valence electrons. And that leads us to what is called the Lewis dot structure. In a Lewis dot structure, we represent the electrons around an atom using dots. For example, let us assume you are asked to write the Lewis dot structure for NH3, that is ammonia. So nitrogen has 5 valence electrons, and we said it has a bonding capacity of 3, so it's going to bond to another atom. In this case, we have hydrogen, hydrogen, hydrogen. So these are bonding pairs. So we call that a bonding pair. Bonding pair is what we represent using a line. These ones here are lone pairs. So that is a lone pair of electrons. So we can simply write the structure of ammonia like that. Let us look at another one, assuming you are asked to write the structure for CH2O. So we're going to start with a carbon bonded to oxygen. Now we have 2 hydrogen atoms. Carbon is already bonded to oxygen. Carbon has a bonding capacity of 2, so it needs more. So we can put the hydrogens here. Oxygen needs to have 2 bonds because we said it has a bonding capacity of 2. So we can do that so that carbon is happy and oxygen is also happy. So then we have the Lewis dot structure for CH2O, where the bonding electrons, we just show them as lines. Let us look at another one. Let us do something like let's do C3H8O. So that means we have 3 carbon atoms, 8 hydrogen atoms, and 1 oxygen atom. So we can draw it in different ways. The first one is we could have carbon bonded to carbon, bonded to carbon, bonded to oxygen. 1, 2, 3, 4, 5, 6, 7, and 8. So we include the hydrogen atoms, and now we have the Lewis dot structure. But we can also write this in different ways. The other option is to write carbon connected to carbon connected to oxygen connected to a carbon. So this way oxygen is still happy because it still has a bonding capacity of 2. Then we include the hydrogens, that is total of 8. Oops. Hydrogen, 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 hydrogen. So that is still a correct structure for our compound. Another option is we could have a carbon here connected to another carbon. Now in this case we had it on carbon, or we can assume that was carbon number 1, and then we can have it on carbon number 2. Oxygen bonded to hydrogen. So 1, 2, 3, 4, 5, 6, 7, and 8. Hydrogen, hydrogen, hydrogen. So we have the correct number of hydrogen atoms. So in this case, we can draw 3 different structures for the same chemical formula. When that happens, we call these compounds, we call them constitutional isomers. So constitutional isomers are compounds that have the same chemical formula but different arrangements in terms of connections. So same formula, different arrangements. We call those ones constitutional isomers. Thank you for watching. Have a good one.